This is chapter 11, where we're going to be learning about more advanced topics of linear regression, especially focusing on selecting between models, taking a large model and removing variables till we find a good fitting smaller model. And we'll also be looking at how predictions of models get better as you make the models actually smaller, meaning predictions of data you haven't seen. And finally, we'll be looking at a application of using linear regression to predict as a classifier to predict two different classes of a binary variable. So all of the materials here can be found on this website. There's a link in the notes. You can download the updated course book from this link here. I've got it here. We're going to be focusing on chapter 11, which is going to start around page 271. And you also need to download some materials for this, including a data set. So if you go down on this page to chapter 11 to the supplemental materials, make sure you download both this walkthrough and this data set, survey.csv. If you look, you don't need to download this key, but this tells you the meaning of the different variables in that data set. So it just helps to interpret it. Okay, so once you download that, make sure you put it into a location you can access to. I've put it all in a chapter 11 folder, and so that I can read that data in. And then I've opened up that R file within R. Let me bring that window over. And here it is. Okay, so right now we're going to be looking at a little more advanced topics of regression. So far we've looked at how to make a regression, how to test individual predictors to see if they're significant. And one of the things we talked about for each of those is that testing whether a parameter is significant is the same thing as testing whether the model is any different than the model that doesn't contain that predictor. So it's two different ways of thinking about the same thing, and in fact, at least for the f-test and t-test that are the way you test those, they are identical. They compute exactly the same quantity, and in that case, I think the f test is just the square of the t-test or something like that. The p-value is going to be the same, and everything's exactly the same. So let's look at this survey. I don't know how this got in here. So if we look at dat 1 to 20, that's what I'm storing the survey in. And this is a survey of people in three different groups. There's students, and there's faculty, and there's people working in business. And so there's a number of each of them. They've all answered the survey and asked, here are 10 different properties that we think make for good employees. What are the most important to you? Or when you hire someone, what do you consider the most? And so this isn't about whether these employees are correlated or related to one another. It's whether people think they're important in the ability to hire someone. And so we have a group, which is a categorical variable with 3 levels. And then we have a bunch of other measures. You want someone who's creative, do you want someone who has leadership experience, hand-on experience, ethical experience, and things like that. How important on a scale of 1 to 5. We can look at the summary of these. So here you see group, there are more students than anyone else. There are about 100 people in industry, 65 faculty, and 119 students in this data set. So you might expect that the perceptions of these different groups differ about what's important. And you can see here, well, they all are between 1 and 5, and oftentimes the mean is maybe a little above 3 or even above 4 sometimes. So people might think all of these are important, or on average they're all important. We can look at them visually, the box plot. Let's see. Let me zoom in here, and you can see how a lot of them are sort of 4s out of 5s, and some of them, like people look at multiculturals, maybe not as important overall. So this just summarizes the data, and in fact, it kind of looks weird because the responses are only 1 through 5, the medians are going to be those integers as well. I might want to look to see how they're correlated with one another, and I can do that with pairs. And you can't really tell, right? Because they're all integers, so we get a bunch of points. We'd have to add some noise or something to be able to look at this more visually. So let's just look at the correlations here. If I look up here at the correlations, you can see that across different things, I see correlations in the 17, some that are very low, others that are pretty high. Teaming and leadership are highly correlated. Communication and teaming, these are 3 that are important. So what that means is if somebody put teaming high, they also tended to put communication high, and they also tended to put leadership high. Those correlations are not super strong, they're 0.4. We also see some negative, some small negative values like this and like this, and so on. So there's nothing that's really strongly correlated. The highest correlations are going to be probably these 2. But they're all, except for a few, they're all generally positively correlated. That when people see one, they tend to like the other one as well, like all the others as well. So let's think about this. Let's say that I want to know, does people, like maybe you think that academic is sort of all well-rounded, that it's supposed to incorporate all of these things. And so we want to see if people's perception of academic is sort of, can be predicted by their perceptions of these other things. Or more importantly, what do they think academics is? And if you can show that academics is a combination of a subset of these, that's sort of what people's perception of what academic skill really is. And so we can make a linear model to predict academic based on all of the others, and that's what this does. We can look at this, and we see that we've got an estimate of intercept that just says on average you get 2.4 points for free, and then for every unit of communication, leadership, hands-on, etc., your academic either goes up or goes down. And we see actually a lot of these, it goes down, which means at least a little bit. The higher you do on one of these, the worse you say, the lower you say academics is. The higher you give a rating on one of these, the lower you give academics. And I guess you might expect there's a trade-off, because some people might say, well, I'm really looking for someone with academic experience, and maybe these are, faculty who are looking for graduate students. And other people are saying, well, students are maybe saying, I'm really looking for multicultural experience and not academic experience. So if you give high on this, you may be likely to give a lower one on academic. We also see that if we look at the t-tests, they are not all significant, which means there's some in here that probably shouldn't be in there. And so what we'd maybe like to do is ask, are there any versions of, and are there any smaller versions of this model that are still good at predicting? Actually, what we'd really like to know first is, if you look at the residuals here, they're fairly equally balanced, so maybe the residuals are okay. They're not too skewed. I'd like to look at those before I go too much further. And if we look at multiple R squared and adjusted R squared, that's actually pretty low. So you have to recognize that in this data set, we're looking at 10% of the variance roughly. There's still a lot of answers in here that aren't going to be predicted by the model, at least this model. So maybe there's, there could be completely different answers given by industry and students and faculty, but we're treating them just as a sort of addition or subtraction from the mean, for example. So I'd like to maybe look at a smaller model, because if there's things in here that aren't predictive, then I'm going to be adding sort of garbage to the model that doesn't belong there. So the goal of the process is to try to remove anything that is not predictive, so that we can get down to the smallest model that is still useful. But the problem is I can't just remove everything that doesn't have a star by it, because it could be that, well, first of all, these are categorical, so we can only remove group as a whole. But if we look at these, or these or something, I might say, let me remove the ones with the biggest p-values. Maybe that's reasonable to do. But you don't want to remove all of them with p-values greater than 0.05 or something, because maybe if you remove this one might be, we know that these are all correlated with one another, so maybe leadership is correlated with multicultural in a way, and they're sort of fighting it out to account for the same variability. And if I remove the worst one, the better one will now account for enough variability that I'm guessing, I would assume that it's not happening by chance. So you sort of want to remove one at a time to get down to the smaller models. So if you think about all of these models, we could take this model and compare it or examine all the neighbor models, the models that we get by dropping one or another one of these variables. I could do this by hand by picking out, well, here's model 2 where I'm going to take and I'm going to remove hands-on, and I'm going to remove, I removed two things. I removed teaming and hands-on. These looked like the smallest. No. Did I remove teaming? No, I kept teaming. I removed leadership and hands-on. So leadership has the smallest t-value, and hands-on is similarly small t-value, large p-value. Well, how did I get there? One way to do it is to use drop one. Drop one takes any model, and it will show me, and if I give it drop one with the test is equal to f, it does a couple things. It shows me all of the models, all the models look like when we remove one of these variables. So now we can look here. Communication, what happens when we remove it? Well, it says communication accounted for 2.7 sum of square units of error. Here's the total residual standard error, and you can see in comparison to the larger model, it goes up. It has this AIC score, which we'll talk about a little bit. And then it has an F value. So it's really saying the F test is a test of two different models, and it's testing the large model against this smaller model. And it's saying for communication, these are significantly different, which means the thing when I take communication out, it gets significantly worse, and I wouldn't want to do that. So what happens when I remove other values? So I remove leadership, my residual R squared only goes down by 0.07. It is almost the same as this, or it only goes up by 0.07. And we say, well, that is not a significant difference. It's got a small f value, a large p value. And so this would be worthwhile removing. Now, if you look here, and then you look way up here for leadership, you see that we get exactly the same p-value. And if you take if you take 0.325 and square it, we get the f value is the same. So really this is doing exactly the same test as this was, but here we're interpreting it as a one sample t-test. Is the mean of communication different from 0? And here we're interpreting it as an f-test. Is the model with that parameter different than the model without the parameter? And I showed you before how we can actually, from this, compute t-value, and now I showed you how from the t-value you can compute the f-value. They're really the same thing. They sort of masquerade as one another. So drop one will give me all possible models that are one away. The nice thing here is it removes group as a whole rather than looking at each one. So if I have multiple categorical variables, I can see their effect on its own. I can't remove group industry on its own from the predictor. I either have group or I don't have group. And this tells me that would be important. So I can then use this to guide my way through a model selection process. So here, I'm just to shortcut it, I'm going to drop two things and call it model 2. and look at the results. And now we can look at, we still have, so now teaming, let's see, teaming before was highly significant. And now curiously, and I guess it wasn't highly, it was about 0.05. And now teaming goes above the 0.05 threshold. The estimate of teaming, oh, I don't see it here, but the estimate of teaming doesn't change much. But the t-value, f-value probably does a little bit. For teaming, the t-value changes a little bit. So what will happen when you remove variables is the other variables will account for different amounts of variance, and sometimes they won't be significant anymore, other times they will. So we want to repeat this process again on this, and we say, well, now if we do drop 1 on model 2, where this was on LM2, I can see, well, multicultural is not significantly different than this model. Creative is not significantly different than this model, but the others are. So the logic here is that if the models are significantly different, then it's worthwhile adding this additional parameter. If there's no significant difference, then we would prefer the smaller model because it's simpler and they don't predict any different in the outcome. So this all these f-tests are done sort of automatically with the drop 1, but I can always compare any specific pairing with the ANOVA function. So now I have LM1 versus LM2, and I do ANOVA, and it tells me for model 1 versus model 2, here's an f value. It's going to be on 2,273 degrees of freedom, and the f value is this, and the p value is this. So drop 1 is sort of a shortcut to doing this a lot. What I find here when I do drop 1 on multicultural 2 is that, or I'm sorry, on model 2, is that multicultural is not adding stuff very much. So let's build a third model. And I can look at the summary of that. Now remember, summary and drop 1 are both basically the same thing, but they look at a different test that turns out to be equivalent. Now each of these is maybe not significant, but they're all marginally significant. Maybe I'm going to be satisfied with this, or maybe I want to go further and remove teaming or teamwork. I could look at, let's see, that is model 3. I could look at drop 1 of model 3, and we see the same p-values. I could test model 1 versus model 3 and see is removing all these things any worse, and it's not. And maybe I want to go one step further because teaming seems like it's sort of marginally predictive. And so I could also do ANOVA or summary of LM4. And now creative doesn't seem to be accounting for very much even now, whereas before it seemed to be accounting for maybe a little more. And you can see how by removing things, we may actually, if the interactions between these are important, we may be removing other things, and they kind of move around a little bit. So I could continue this until I get a model that I'm happy with. But if we look at, you have to recognize though that our adjusted R squared or our multiple R squared, here it's 0.1034. For model 3, it was 0.1134. So maybe there's a 10% difference in multiple R squared, but it's all very small. So you're dealing with very small proportions. So even losing these marginally predictive things is not going to lose you a lot in terms of if you're trying to predict things, because the model's really not that great. Well, let's look at a bunch of other models. I'll define sort of a sequence of these models from maybe just continue. If I continued this process, I would remove the worst one each time until I got down to just a single one. So I showed you how you can compare a pair of models with ANOVA. We can compare a bunch of them with ANOVA, and this is going to give me sort of the f-test of each consecutive one. So you see every time I remove one model, the degrees of freedom goes down, and so this is sort of like a tree of models or a hierarchy of models. Every time removing one or more variables, first I was removing 2 variables, and then I removed 1 until I got down to just prior work plus group. Model 7 was just group, and then here's the intercept only. And now we could think about every time I remove one, I can see, well, you can think about it from the bottom. Every additional variable I add, am I gaining anything? And you might be satisfied with model 6 because adding the additional variable of model 5, which is communication, is not significantly better at a 0.05 level. So here is just a set of models, and we might say by removing variables in this order, we're getting down to the most predictive model, that we only are keeping things that really matter. And now if we look at that model 6, model 6, I called it LM6. We can see, the multiplier squared is 0.074, adjusted as 0.06, whereas the LM1 was 0.12 and adjusted R squared is 0.09. So we are maybe getting substantially worse in our modeling here in the fit of the model when we go down that far. But possibly what we're losing is just things that are not really part of the data, but just predicting additional noise. And so the hope would be that by doing this, we find a true model and get rid of all the other stuff. But we actually often never really know. So you can do this hierarchy of however you want, compare any pairs or any sets of models, and test them against one another. So another thing to do would be to say, well, if we were happy with 6, is 6 any worse than 1? Here's asking if 5 is any worse than 1. So is 6 any worse than 1? And in fact, 6, it says that we can do better than 6 by adding everything else back in. So even though for each individual thing we remove, it wasn't getting any worse, sort of all the combined pieces make it worse, and so maybe we would want to go back up to model 5. All right, so that's sort of the ANOVA or t-test approach for variable selection, and you should just recognize that variable selection is the same as model selection or model testing and model comparison, and it's the same thing as testing whether parameters are significant in a t-test. Now this whole ANOVA approach sort of relies on the logic that these are nested, because it's like the same model plus additional parameters. One model has all the things in one model plus additional stuff, and so if you find that the 2 models don't make any different predictions or significantly different predictions, then you would say, well, I'm going to be happy with the smaller model. I'm going to choose the simpler model just because I like simpler models. But it's a little different if you've got 2 models that aren't nested. So here are 2 models that are not nested. They both have an intercept, but one is communication and one is creative. And now they both have the same number of predictors. So there isn't really an ANOVA test here to do. If I try to do an ANOVA, it'll give me my residual sum of squares, but there's no difference in my degrees of freedom. There's a difference in sum of squares, so there's no f-test associated with this. I need a change in this to compute the f-test. But that's fine because in this case, you would just see which one has the better residual sum of squares. You could use the same logic and say, well, here's 2 models that are of equivalent size, and if I had to pick one, I would pick model 1 because it has a lower error than model 2. So you can't do the ANOVA, but you can use the same logic in those cases. Okay, so when we're doing this drop one, we'll look back here, there was also this column called AIC. So AIC gives an alternate way of testing and comparing models. It's different than this f-test, and the AIC statistic, first of all, looks at log likelihood. And so if the model's better, it has a higher log likelihood. And the way it frames it is negative log likelihood. So if the model's better, it has a lower AIC, a more negative AIC. But then it also punishes you for having more parameters. So this is sort of an implementation of Occam's razor, where you ask, I only want a more complicated model if the additional complication is worth it, if it pays for it itself. And the AIC is one way of looking at that. And so you can see here that rather than having to do this test, and because the residual sum of squares is always going to go down when we add more parameters, it's always going to go up when we remove parameters. The AIC tries to balance these against one another in a systematic way. So you can see here that prior work was very important, and it says, well, when I remove prior work from the model, my AIC gets much more positive, which is worse, and so I wouldn't want to remove this. This model, the model without prior work, is worse than my current model. So that prior work predictor pays for itself. But we also see here that there's, here's communication. It's more positive or less negative than this, so this is a good one. But this is more negative, so this would say leadership and hands-on. Anything lower than 102, I can get rid of. And there's 4 of them there. Those happen to map onto the same 4 that are not significant. It's not always going to be that way, but it's often going to be quite similar. Sometimes it'll be marginally significant here, but this will always give you, a direct comparison between 2 models, and it'll always give, whichever one is even just a little better is the one you pick. So if you use drop 1, it will give you those AIC values, and you could, instead of using the f-test logic of saying, oh, is the smaller model better, you could always just use the AIC and say, I'm going to use whichever neighboring model it has a better AIC score. So if we go back here, I can take all those same models we created and make a table of all of the AIC. So this is one model with all the predictors, and it scores AIC for every adjacent model. So every model without communication, model without leadership, model without hands-on. But now I've gone through and I removed them one at a time, right, before, and I can look at this sequence of models as I remove the worst predictor in each case, what happens. And now I start out with 102, and by removing the next one I get better, and the next one I get a little better, and then I start getting worse again, and worse and worse. And so I would want to pick this model according to the AIC, whereas before I was sort of stuck between somewhere in these models, depending on if I wanted to use a 0.05 value or not. And then when I got down to here, I decided that actually this one, even though it was no worse than this, and this one was no worse than this one was worse than this, so I wanted to back up a little bit. Well, this gives us a different stopping point and says model 3 is the best stopping point. It has the most negative AIC value, and so this is the one we should use. So this is a second method for model comparison and model selection. And in this case, just like before, you're not testing what, you're no longer testing whether a coefficient is significantly different from 0. You're taking one model and you're comparing it to another model. Those models differ by one or more variables. In this case, it's usually one variable. And we're asking which of these two has a better AIC score, this information criteria score. So this is a pretty common method for doing variable selection. But there's maybe even a more popular one that Schwartz came up with in the 70s based on I think AIC was first and Schwartz came up with this one afterwards, but they both arose 30 or 40 years ago, and it's called the BIC, the Bayesian Information Criteria. So Schwartz figured out and proved that the information, if you have the number of parameters that you want to use, it's got to sort of depend on how much data you have as well. So if you have a really large data set, you can afford to have more parameters than if you have a very small data set. And if you have only a few data points, you should be really reluctant to add additional parameters. And so there's some Bayesian logic behind this. And so, but there's not like, when you end up computing this, there's not Bayes formula in there. What you do is you adjust a certain parameter of the AIC, where the AIC needs to consider k as equal to 2. The BIC considers k as equal to related to the log of the number of data points you have. So there are some libraries that will compute BIC for you, but AIC, the function extract AIC, is in the base library, and you can create BIC just like this. Feed it a linear model, and it will, and here's a formula to do that. So I'm going to run the same table here with BIC scores and see what happens. So now these values they're not going to map onto these values in any meaningful way, but the interpretation is still the same. So here we start at -102, here we start at 66, and it gets better, and it gets better, and it gets better, and then it starts getting, it gets better and gets better and better and better and better, and then it starts getting worse. So in this case, -86 is the best model that we end up getting according to BIC, and it ends up being model 5, which is smaller than what we got with the AIC. The AIC said, oh, we should use model 3, which has more parameters in it than model 5. And this is sort of like what we got when we did the F-test, but the F-test was sort of ambivalent between these two, and when we got to this one, we said, well, it's no different from this, but it is different from up here. So this gives us maybe an easier decision process. We can just look at the BIC. In general, because the BIC also considers the number of the number of data points you have, it's going to be more conservative than the AIC. So it's going to tend to prefer smaller numbers of points. Now there may be I don't know if you have a really, really large data set. It might be that the BIC will like more complicated models. I'm not quite sure. But in general, whenever I've played the two against one another, the BIC always is a little more conservative, because you need to have additional data points for every additional parameter you add. Okay, so the AIC and BIC are two alternative ways of evaluating models that balance the complexity of the model against the goodness of fit. And the logic's a little different than the t-test or f-test approach to model selection, but you still have this notion that you have a pairing of models, they differ in some way, and you have a way of evaluating how good the model is, and you want to choose which one is better. And then we sort of think, well, if they're no different, then in whatever ways those two models differ, if they're no different in their goodness of fit, whatever ways those two models differ is not important. This can be a little tedious, and you might think, well, what I want to do is some type of stepwise process where what I'm doing sort of manually is taking the worst one out each time, and then looking at that model, taking the worst one out each time, and using some type of logic to do that. And so there's a function called step right here, and there's a related one within, I think it's either the mass library or the car library called Step AIC, which does a similar thing to this, that will do a stepwise regression. So it will start at for a certain model, and you may have to specify the smallest model as well. It just depends on how you want to do it. And then it will iteratively remove variables one at a time until it finds the smallest model that has the best score according to whatever measure you want to specify. And so STEP uses AIC but allows you to specify K. This is how you'd specify the BIC. As long as it's LM1 use DAT, this is the K value to use. It's the number of observations in the model. So you can do stepwise in three ways. One is you can start with the most complex model and remove variables one at a time. Another is you can start at the smallest model and add them one at a time. So if you do that, you have to sort of specify the smallest and largest model you want to consider here. And this might be an alternate way of going about it. And the reason why these differ is because as you add variables, the number of models you're considering just explodes. You get more and more and more possible models within this space, and once you get enough predictors, you're never going to be able to explore all of them. And so you need to find a way to explore them in a way that is likely to find the best model. So direction here, if you want to use, let's look at what step. Both backward and forward will either go larger or go smaller, and but both is interesting because at every step it looks at all the models that are one larger and all the models that are one smaller and picks the best out of all of these. So you might find that, like, we sort of saw that some predictors seem to be correlated with one another, and if we removed one, then another one got worse. So you might find that after you remove one, another variable that you removed previously makes the fit better because they are correlated. And even though on its own removing it seemed reasonable, there's some interaction that makes it unreasonable. So in terms of direction, I like to use both. It takes a little longer because at every opportunity you have to test more models, but oftentimes it's less likely to get stuck in sort of one chain. And it will find, because at every model it looks both at the models that are more complicated and less complicated. So this would be like almost a staircase method or a bidirectional stepwise regression. So I can use this same logic, and you can see, because by default traces on, it tells me each step. And if you have a lot of variables, 30, 40 variables, which I've sometimes had, this could run for half an hour, and it keeps on spitting out models, and you can see as it's moving through how it's moving through the space. And every time the AIC is going to get better as it compares either adding or subtracting. So at every step, it says I'm going to look at how each of these AIC models when I remove one, and then I'm going to look at what happens when I add the ones that I'm not using to see if those improve it. And you can see, well, when it gets to the end, every single neighboring model is worse than this model. And if we look at G small, this ends up being communication, prior work, and group, which I think is the same thing we found for model 6. Communication, prior work, and group. That's model 5 it ends up with at the end of the day. Okay, so we covered sort of using f-test and t-test for model comparison, model selection, and removing variables. That's possible. What's probably a better approach is to use an information criteria, and the BIC is probably generally a good one. It's a little more conservative than the AIC. It will usually pick a smaller model than the AIC does. But of course, we've also looked a little bit at Bayes factor approaches, which is not exactly the same as BIC. It's going to give a different measure. So if we load Bayes factor, any one of these models we can fit with an LMBF, and we can get a Bayes factor out of it. Actually, there's a way of plotting it. The plot doesn't really often show much. But here's two particular models, and if I want to see if they differ, just like I could use a BIC criterion, I can use the Bayes factor, and I can pick, make my decision based on the Bayes factor. And so here I would prefer this smaller one over the larger one because it's 14.9 times more likely. So I can do this by hand by crafting, just like I did up here, a set of nested models and see how the Bayes factor logic works. In fact, let's look at, we ended up settling on maybe model 5 as the best one according to the Bayesian information criteria. So what if we fit this? All we need to do is say LMBF, and I'll change it to B5. And now if I do B5 over B1, it still thinks that this smaller one is much better than B1 alone. If I do B6, because remember in the Bayes factor, in the BIC, we thought that, I think we thought that B5 was better than B6. I can do this, and then I can say B6 over B5 and see what it says. And now it prefers the more complicated model over the simpler model. It says adding communication really does improve it by a factor of about 3. And so here you would probably just use 1 as your criteria and choose whichever one's simpler. But really there's pretty strong evidence this is more than 3 to 1 in favor of this over this. So it's not even that you're ambivalent. You have a pretty strong evidence for this guy in comparison to this guy. Now, LMBF will handle one model at a time, but we looked at this previously. We can do a whole regression of all the predictors, and it will compare all submodels. The only problem is regression BF doesn't handle categorical predictors. It won't handle that group. We could figure out a way of doing that by doing some coding of group into linear predictors, but I'm not going to do that. I'm just going to look at remove group and look at the predictors. So this takes a while longer because it's actually comparing dozens and dozens of models. And the plot is not going to show much because it's going to show a bunch of potential models. I chose the head of B model. If we look at B model, there's 127 possible models, and we want to look at all of them. And so if you do head of B model or head of B model, I could look at the best 10. It will show me the best ones, overall best models in comparison to the intercept-only model in terms of Bayes factor. So this is the best model overall of all the possible submodels. And so this is the one we choose: teaming, prior work in creative, and communication, which may be a little different than B6, but it also doesn't have group in it. And so we're sort of maybe accounting for some aspects of group by this on its own. Okay, so you could use, for model selection, to figure out which predictors, you could use a Bayes factor. And this is really easy to use, maybe even easier to use than the step function. And if it just can't take categorical predictors, which means you might have to do some stuff by hand to do this. But the Bayes factor is pretty easy to use as well. Okay, so those are some methods for selection. We're going to look at sort of one other approach in this next section, which is about cross-validation. Now, previously we had talked about in a previous chapter how you can make predictions from models. So here's a model, and I'm looking at digit span, it's a measure of your memory, and I want to see if it's related to age and income. And of course, I'm just making these data up. But I can plot this data with respect to income and age, and you look at digit span, how long of a list of numbers can you remember immediately? And some people can do 6, and some people can do 10, and a few people can do 14. And I've plotted here, if you can see it, the model's best predicted point. So we can see that it looks like it has a strong relationship to income, for whatever that means. It does, and you don't see a strong relationship with age here, although it exists. It's just sort of masked by the relationship of income. And if we looked at these together, we probably could see these lie on a plane. So just looking at things with respect to one dimension doesn't always show the relationship that really exists. But if we look at observed versus predicted, we get a pretty strong relationship. And so we fit a model, and we can see, in fact, both age and income are significant predictors. The intercept is actually not different from 0, but it's not clear that that is meaningful at all. Overall, we have a relatively large multiple R squared, so that's good. We're accounting for a lot of aspects of the data. The model is different from the intercept-only model, and so on. All of those things are things you know how to do. But just think about, we can see what the fitted values are, and I plotted those earlier, and we could get those from predict. That's the same thing. I can prove they're the same by correlating them. The correlation is 1. But now recognize that I can, if I know, if I go back to this plot, if I know age and income, I can put these together and make a prediction about digit span. And I do that with the predict method for model. And I give it either a list or a data frame containing the names of the variables. So here, if someone's 30 and I had an income of 10,000, that's what I expect. And if they're 30 and have an income of 40,000, that's what I would expect their digit span to be. So we know how to make predictions, but this is a model that we fit based on the two things we created with, and it was pretty good. We almost never know what all the good predictors of our outcome are. And we often have predictors that aren't any good, and that's why we do this variable selection and then this testing. So what happens if we have sort of a bad model? So here is a bunch of predictors, categorical and continuous. And then I'm going to create an outcome I'll call y that's related to one of the categoricals plus 2 of the predictors. So xcat and x2 and x3, but the others are not related, and they have different forms. And but supposedly we don't know which are the right ones that are predictive. So I'm going to make a data frame that contains all of these and then just build a model. If I look at the model, well, we knew these category is predictive, x2 and x3 are predictive, and it also thinks x7 is predictive for some reason. It's not nearly as strong, but it's there. But that was just bad luck. We are doing 1, 2, 3, 4, 5, 6, 7, 8. We are doing 9, and so with an alpha of 0.05, we'd expect a pretty good odds of seeing one of these just by chance, because if we use a 0.05 criteria. Overall, the R squared is pretty good. The multiple R squared is pretty good as well. And so I could take this and make predictions about the data. And I could look at how good I predict that data, 0.0847, that's what we saw in the R squared. Or I can make a prediction about new data. It says, well, that's what my new data should be. Well, if I use just one of these points, or I could take, I could take this and I could change the category to B and say, well, what would happen if this same person was a category B? What would it look like? And I can make that prediction. Or I could do a completely new data set. I could give it all the values I care about. It says, well, if this outcome Y had all of these X values, this should be the right answer. But remember, these are the only three that really matter in reality. These are all garbage that aren't really helping us, but they're changing the prediction. So let's say that through the model selection process, we were able to trim this down somewhat. Well, first, how would we know if we're doing good at all? So as I discuss in the chapter, one way to test this for model selection is through a cross-validation process. And so if I take, I have got, what was N here? I've got 50 points. That's not a lot for a model. This is not the data. That's not a lot for the model. But I could say, well, what if I picked 25 of these, a random 25, and this is just picking randomly 25 of them, and picked that set and fit my model on that. So here's the same model, but it's fit only on half of the data. And now let's say I did some model selection and I got down to the right model. I happened to get down to this model, which was true, but who knows if you'd really get down to that. I probably would have retained 7 in there even though it didn't belong, because 7 was a significant predictor. So here's another one. So model B is just like model A, but it's only fit on half of the data set. And model C is fit on the same half of the data set, but it's much smaller. So we looked at model A, we see a multiple R squared of 0.9. And here we see a multiple R squared that's even higher. And here we see a multiple R squared that's about 0.9 as well. It's not going to be as good as model B because I have fewer predictors. So in each of these cases, we think we're doing pretty well. I could pull out the coefficients of each model and look at them. So here I pulled out the coefficients. Here is my original model fit on the whole data set. Here's the true model. I created it, so I know this, and you can see how accurate these are. This is what happens when I fit the whole data set on only half the data. And you can see these values are going to differ from this large one, and they're going to differ from the truth. And here's where I fit the smaller one on these. And you can see now that, well, here, if we compare just 2 to 3 and look at the truth, for category A, it's closer. For category B, it's closer. For category C, it's closer. Here, it's for X2, it's further away. Here, it's about the same. And because I've managed to force these to be 0, it's identical in these cases, and these are adding stuff. So not only are we getting in this model 2, we're getting some of these wrong, we're also adding other stuff because they are compensating for each other. So what happens if we look at the goodness of fit of these? So here's that original model. It's fit on the whole data set. And if I fit it on the first half of the data set, if I look at the goodness of fit of the first half versus the second half, well, they differ a little bit. There's no reason why this should be better because it was fit on the whole data set. But for this split, the first half is fit a little better than the second half. But now if I look at the second model, which is the same complex model, but fitted only on the first half, I see that it fits a little better. But then that second half, which it wasn't fit on, the fit is worse. And so that's what you will typically see. I mean, it's not just that 0.9 is different than 0.7, but it's that 0.82 is different than 0.7. So the second half goes down. But if I take that smaller model that I've selected, just a good model, well, now the smaller model is worse here. I'm not fitting as well because I don't have as many predictors, and there's really no way for this to go up by doing this because I'm fitting. This is the data I'm fitting on. But if I look at the new data set, now this is about the same as my original, and it's much better than this. So this is just an example that if you're using the model for prediction, having a more complex model is not going to help if it includes variables that are not predictive, because if you're then trying to predict things you're going to make mistakes. You're going to use values that don't have an influence to make the prediction, and depending on what those values are, it could have huge effects on the ultimate thing you predict. I mean, this is just values that are within the range, but if you take things outside the range, those could have a huge impact. Okay, so this is a cross-validation method and demonstrates the value of sort of removing the parameters. And I'm not going to go through this in great detail. This is all the detail I'm going through it. But instead of using BIC or Bayes, you could also generate some cross-validation measures. You might have to do it a little more systematically, sort of maybe splitting your data in half hundreds and hundreds of times and doing this multiple times to see is this additional parameter worthwhile in all the different ways we could split it. And so is it really increasing the fit of the left out data? And if you're then really doing prediction, you don't know what the answer is, and so you'd like to split your data in halves, or at least maybe instead of in half you do 10 to 1, or you do leave one out, so you fit the model a bunch of times, leaving one out at a time, and fitting that resulting model with that one that wasn't used as part of the prediction. So there's a lot of ways of doing this type of cross-generalization, and cross-validation methods. And they are really kind of another alternative to either doing f-tests or AIC or BIC or a Bayes factor test. Okay, the last piece is now we've used categorical predictors, but what about categorical outcomes? What about if you have categorical categories that you want to make a prediction about? This is a little trickier, and it generally will get a lot trickier if you have more than two categories. But if you only have two categories, it's actually pretty simple. All you really need to do is, if you have two categories, is convert these to numbers and build a model. And then, but now when you make a prediction, it's not going to make a prediction about the particular value, and so you're going to have to use some decision criteria to categorize it. So here's a case where we might know that the gender of people, and we know that both height and weight depend on gender in some way. And if we plot height and weight against one another and then plot gender as the color, we can see that there's a nice line here that will do really good at discriminating the two. So if we build a model predicting gender, I'm going to convert gender to numeric. If I do gender, if I do as numeric gender, it recodes these as 1s and 2s. So really I'm just predicting 1 and 2 based on height and weight. And I look at the model and it looks just normal. And if I look at the fitted values of the model and I plot it, it plots it as a bar plot, you can see that they take on values from 0.8 to about 0.2. And because I'm predicting values of 1 or 2, I could just round these to the nearest value, or I could use 1.5 as my criteria. Anything below 1.5 I'll call female, and everything above 1.5 I'll call male. Here's the actual points, and 1.5 turns out to be a reasonable criteria for this. There might be other concerns that you might want to adjust that by, but let's just use 1.5 here as our predictor decision. So if in each case I can make instead of saying my gender is 1.8, I could just say if you're greater than 1.5, I'm going to call you male, and if you're less than 1.5, I'll call you female. We can make a table to see how good the prediction is. And here's the real gender, and here's a predicted gender, and about 20 out of 25 cases, or 41 out of 50 cases, I'm correct. So that gives me, I don't have a goodness of fit anymore really, but I've got this table here, and I can use the error rate to figure out if the model's getting any better. So there's an example like this on the problem set, and so by making this table, you can see by adding more parameters, am I able to get better? maybe I can get down to 3 errors. By removing parameters, maybe I get worse. And if you have this table and you want to figure out sort of how good it is, you can do diag of this, which will give you the values on the diag, and you could do sum of diag, and this will give you a single criteria of how many did I get correct. I could divide by 50 or whatever number, and I'm 82% correct. All right, so the only thing left in this is an example that we're going to work through in class, but this is sort of an example that does a fairly complicated regression model, a lot of different tests and a lot of different thoughts about how to model growth rate over time in the chick weight data set that we've actually looked at in a previous chapter, maybe chapter 3, when we just plotted it. Now we're going to look at it in terms of a linear regression model. All right, so that is it for this chapter. Stay tuned for the next chapter where we're going to be talking about orthogonality and how different predictors fit together to form more complicated models. And so stay tuned. Thank you.